Hello students, and welcome to Topic 9 of Alternative and Renewable Energy Sources. The topic we will be covering is solar thermal systems and components. This topic lecture is broken into two parts. This is part 2. There are a variety of hot water storage tanks, 3 of which are shown here. The tank on the left is a simple storage tank without a heat exchanger. Its function is simply to store hot water. The storage tank in the middle has a heat exchanger close to the bottom. This would be used in an indirect solar thermal hot water system. The tank on the right has 2 heating elements. One heat exchanger low in the tank to be used the same as the heat exchanger presented in the middle tank, and the heat exchanger high in the tank to be used to heat water with an auxiliary source of heat. Conventional water heaters are designed to encourage mixing of water to produce a full tank of hot water. Natural gas and propane water heaters have their burners located at the bottom of the tank to encourage this mixing. Electric water heaters have 2 heating elements, one at the bottom and one in the upper third of the tank. Here is shown in slide 4 a conventional electric water heater with 2 heating elements. This slide shows a single electric solar storage tank with 1 heating element. With close examination of the picture, we see that the water going to the collector is drawn from the bottom of the tank where the water is the coolest. The hot water returning from the solar collector enters the tank in the upper portion. Cold water supply enters the bottom of the tank, and hot water to be used is drawn off of the top of the tank. All of this promotes stratification of the water in the tank. The 2-tank system as described is a more common type. The first tank has a heat exchanger and the water is heated by the solar thermal collector. This tank then supplies preheated water to the second and regular water heater. This configuration allows, when the water is not heated to the desired temperature by the solar thermal collector, the water will be heated to the desired temperature in the second and regular water heater. A picture of the 2-tank system described is shown here. Indirect systems have heat exchangers which transfer the heat from the heat transfer fluid to the potable water. The heat exchanger can be either internal or external. The upper tank has an internal type heat exchanger. The lower tank has an external flat plate heat exchanger. The internal heat exchanger requires only 1 pump. The external heat exchanger may require 2 pumps or may have 1 pump to the solar thermal module and depend upon thermal siphon to circulate the water through the second storage tank. The heat exchanger shown here is referred to as a sidearm. The solar thermal fluid from the module is pumped down through the inner tube of the heat exchanger. The exterior tube circulates water through the storage tank, relying on thermal siphon. Heat exchanger shown here is a flat plate exchanger. A number of plates can be added to produce the required size of heat exchanger. The flat plate heat exchanger is shown in its operating position. This would require 2 pumps, one to pump fluid through the storage tank and onto the pump fluid through the solar thermal module. Selecting the right pump for the solar thermal system is not as simple of a task. The choices are many: AC or DC, powered, bronze, stainless steel, iron or plastic, high, medium, or low head pressures. Pumps used in solar thermal systems are also referred to as hot water circulators. Pumps are made of 3 parts: a motor, impeller housing. The motor rotates the impeller to move the liquid by centrifugal force. Circulating pumps must be primed or wet in industry to speak when they start. They are not designed to suck fluid into them. Unlike positive displacement pumps, which can lift a fluid from below the pump, circulating pumps must have the impeller housing filled with circulating fluid at all times. Hot water circulators are a must-have for an active type solar thermal system. Common circulator pumps have maximum service temperatures of approximately 140 degrees Fahrenheit, but almost all are rated above 200 degrees Fahrenheit. The slide shows an external flat plate heat exchanger with the required 2 pumps. It also shows an optional circulating pump to circulate water through the home or facility. This allows for hot water to be very close to the faucet and eliminates the usual wait time. Here is shown the drain back system. The pump is required to have a high pressure capabilities at startup. The pump must push water to the top of the solar thermal collector during startup. After startup, the pump is only required to provide the standard pressure. There must be some method to control the pump. The controller must determine when there is sufficient solar energy available at the collector and then activate the pump. As stated here, there are 3 popular types of controllers: the differential temperature controller, the photovoltaic controller, and the timer controller. The differential temperature controller works in conjunction with 2 temperature sensors. One temperature sensor near the hottest point on the collector and 1 temperature sensor at the bottom of the storage tank. As stated here, the temperature difference between the 2 locations can be between 5 to 20 degrees Fahrenheit. When this temperature difference is met, the pump will turn on. This explains the operation of the temperature differential pump controller. When the installation uses forced circulation, it is also necessary to use control system based on operating fluid temperature at the collector outlet and at the bottom of the tank. Special attention should be given to proper sensor installation and precise temperature measurement of the 2 sensors. A control device should be used that includes a display, which allows the values most significant to the system operation. In any case, it is interesting to note the temperature of the fluid available for consumption. The system shown differs from the direct pump system in that energy to power the pump is provided by a photovoltaic panel. The PV panel converts sunlight into electricity, which in turn drives a direct current pump. In this way, water flows through the collector only when the sun is shining. The DC pump and PV panel must be suitably matched to ensure proper performance. The pump starts when there is sufficient solar radiation available to heat the solar collector. It shuts off later in the day when the available solar energy diminishes. The timer controller in this slide is set to operate during a period of the day when solar radiation is available to heat the potable water. In order to avoid loss of energy from the tank during overcast days, the collector, feed, and return lines are both connected at the bottom of the storage tank with a special valve. During normal operation, natural stratification allows the warmer water to rise to the top of the tank. This control method uses tropical climates. This control method is used in tropical climates where temperatures are mild year-round and significant amounts of solar energy are available almost every day. In a timer controller system, a timer turns on a pump in mid-morning and switches it off in late afternoon. To ensure that the heated water stratifies to the top of the storage tank, the system uses a very small pump. The collector feed and return lines are both connected through the use of special valves at the bottom of the storage tank, so only the coldest water from the tank flows through the solar collector. The timer systems could conceivably operate during rain or overcast conditions, so care must be taken to ensure the proper supply and return lines to the collector are located near the bottom of the storage tank. Therefore, if the pump operates during a cloudy day, only a small amount of the water at the very bottom of the tank will be circulated through the collector. This prevents potential major tank heat loss. The expansion vessel is a tank divided into two parts by an elastic membrane. On one side of the membrane is a corresponding operating fluid, normally water in a liquid state, and on the other side is air or an inert gas pressurized to the working pressure. The initial pressure is established at the factory and may be adjusted later during installation. The main function of the expansion vessel is to absorb the variation in the operating fluid volume during the changes in its temperature. The minimal expansion volume will be the total volume of the solar collectors and will vary on the use of the installation. It is convenient to take into account the vapor generation due to stagnation when sizing the expansion vessel. All solar systems use some type of heat transfer fluid. Potable water in the heat transfer fluid is active directed systems and is most common. Indirect systems in cold climates use a non-potable solution that will freeze only at extremely low temperatures. The most common types of these fluids are polyethylene glycol, ethylene glycol, hydrocarbon oils, synthetic oils such as silicon. Some of these fluids are toxic and require double-wall heat exchangers. The Food and Drug Administration has classified propylene glycol as generally recognized as safe, which means it is acceptable for use in flavorings, drugs, and cosmetics as a direct food additive. Pipe insulation is shown here. The most common type of pipe insulation used in solar systems is a closed cell, flexible, elastomeric foam type rubber, commonly marked as Rubitex or Armatex. Plastic insulation such as polystyrene or polyethylene should never be used to their low operating temperatures. All external piping insulation must be protected from environmental and ultraviolet ray degradation by using special ultraviolet ray-resistant coatings, paints, and/or shielded wrappings. A temperature pressure relief valve is also called a pressure temperature relief valve, or P&T valve, or TNP valve. These names are used interchangeably in the industry. This valve, shown, protects system components from excessive pressures and temperatures. A pressure temperature relief valve is always plumbed to the solar storage as well as the auxiliary tank. A pressure relief valve protects components from excessive pressure that may build up in a system's plumbing. In any system where the collector loop can be isolated from the storage tank, a pressure relief valve must be installed on the collector loop. The pressure rating on the valve, typically 125 psi, must be lower than the pressure rating of all the system components which it is installed to protect. The mixing or tempering valve will mix cold water with the hottest water from the storage tank, delivering water at a preset temperature. Such a valve increases the total amount of hot water available. The intended use of this valve is to conserve water, not as a safety device. A thermostatic mixing valve is a valve that blends hot water with cold water to ensure constant, safe shower and bath outlet temperatures, preventing scalding. There are factors that influence the design of solar thermal systems and its components. These factors may include the amount of water needed to be heated each day, relative costs and inefficiencies, simplicity of operation, and climate conditions. In the United States, a person uses an average of 20 gallons of hot water per day. This is the number that is used in designing a system. If the household has more than 4 persons, the number of gallons per day for that household is reduced by 15%. When designing a system to meet hot water needs, the system is usually not designed to meet 100% of the hot water needs. Doing so would result in the system overheating in the summertime. The systems are usually designed to meet 60 to 75% of the hot water needs. This percentage of hot water which is met by the solar thermal system is referred to as the solar fraction. There are several methods to determine hot water requirements. The first one, which was previously mentioned, is referred to as the formula method. There is also the method of using utility data and also the method of data logging. Here we begin to demonstrate some valuable calculations with respect to solar thermal design. We look at how much energy it would take to heat 50 gallons of water from 55 degrees Fahrenheit to 105 degrees Fahrenheit. Water weighs 8.34 pounds per gallon. Therefore, 50 gallons of water weighs 417 pounds. Water has a specific heat of 1 BTU per pound degree Fahrenheit. 417 pounds multiplied by the temperature difference between 105 degrees Fahrenheit and 55 degrees Fahrenheit, and the specific heat of water, which is 1, yields 20,850 BTUs. The formula method for determining the hot water requirements for a family of 4 is demonstrated. 4 people using 20 gallons of hot water per day each use a total of 80 gallons of hot water. 80 gallons times 8.34 pounds per gallon, the difference between 110 and 58 degrees Fahrenheit, and the specific heat of water gives us 34,694 BTUs per day. This slide demonstrates using natural gas utility data to determine the hot water needs of a family. This household uses 0.5 CCF of natural gas a day. Multiplying the 0.5 CCF times 100 feet cubed per CCF, 1,000 BTUs per cubic foot, and the estimated hot water heater efficiency of 65% yields a requirement of 32,500 BTUs per day. Here we demonstrate the use of data logging on an electric water heater. In this case, 9 kilowatt hours per day are used to heat the water. Taking 9 kilowatt hours per day multiplied by 3,412 BTUs per kilowatt hour gives us 30,708 BTUs per day. If there are any questions, please post them on the eLearn Help discussion.